All right. So today we will keep working on this fun little problem that I'm trying to solve for our friend Dash on Twitter, where we're trying to get the optimal recipe, I call it, basically a list of ingredients and the weight for each ingredient based on a goal for nutrients that we have. So let's say we say, oh, for this meal, I want to eat, 20 grams of fat, 22 grams of protein, and 10 grams of carbs. And here are the ingredients I would like to have in my meal. So apple, which has, 0 grams of fat, 1 gram of protein, 16 grams of carbs, and chicken, which has a different composition in terms of nutrients. So how do we get the optimal weight for each ingredient? And I'm trying to solve this using basically a search algorithm. I'm using the hill climbing algorithm, where you're basically starting off with a random combination, and from there you look at the adjacent combinations. So you just increment, like maybe let's say we're going to keep it simple and keep that example apple and chicken. So let's say you're first starting off, well, let's try 100 grams of apple and 100 grams of chicken. And then you evaluate that compared to the goal you're trying to get. And this is what I'm doing here in this method here, score. I'm basically assigning a score, and it's pretty simple. All I'm doing is I'm totaling the difference between our recipe and the goal we're trying to get to. And I'm not giving any more importance to fat or protein or carbs, but you could easily modify the code to do that. So what we do then is, okay, so we'll figure out that this combination we're trying right now has a distance from our ideal of, let's say, 20. We score at 20, and the goal here is to minimize that number, get it as close as possible to 0. So then what you would do is we would take that randomly generated combination that you start with, and then look at incrementing different things from it. So let's say we only have 2 ingredients here, apple and chicken, and they were both at 100 grams. That's what we started with. Then we would say, okay, well, we could have 101 grams of apple and 100 grams of chicken, or we could have 101 grams of chicken and keep the 100 grams of apple. What would that do? Or you could also lower chicken to 99 grams while keeping apple to 100 grams, or the opposite. So that gives us, in that case, 4 neighbors to our starting combination. Then you would score. That's what we're doing here. And this optimize, oh, actually, this generate neighbors method here is what generates neighbors. It takes in the combination, the recipe as I call it, and then it spews out a list of different recipes or combinations. And here is where the bulk of our algorithm does its work. We're taking in the different neighbors here. See, we're going through all the neighbors, scoring them, and basically keeping the best one. That's what we're doing right now. And we keep going and keep going and keep going. As long as we're improving, we keep going, always finding the next best combination until, whoops, all neighbors will actually give us a worse score. See, and that signifies that we've reached a peak, thus the hill climbing. Well, in our case, since we're trying to get towards 0, it's hill descent, but it's the same principle. Now, this works pretty well. I'm pretty happy with it. If I just go to, let's see, just run my test file here. I think I've set up some dummy stuff. somewhere. Let's see. Yeah, that's right. Okay, so, oh yes, I remember now. So what I did just before going to bed is, this was working really well with just 2 ingredients. As you can imagine, it's a pretty small search space, and it would almost always return the global optimal, the best possible solution for the entire problem. But as you increase the amount of ingredients, well, I'm not always getting the global optimal solution, and that I can show you guys why. If we go to hill climbing algorithm, let's say, probably this. No, show you guys something better than that. Yeah, that's perfect. Okay. Can I get it bigger? Well, whatever. Can I zoom in? How does that work again? There you go. Woo! Not that big. Okay. So let's say because we're starting from a random place. So let's say this is our search space, and we're starting here or here. We would find the best neighbor, which would be along the slope here, and eventually, hey, thanks for following, high five. So eventually would end up at this point here, and it would generate the neighbors, and notice that, oh, all neighbors give me a worse score than what I have right now. So it would return that as being the best combination, the best recipe. But in reality, we're at what we call a local maximum. There is a global maximum. There's a better option out there, and it's right here. But unfortunately, because we started doing our, running our algorithm somewhere here, well, we'll never know about that. So that didn't really happen when I only had the 2 ingredients. But as I'm adding ingredients, I have 4 here. You'll notice, okay, so see here, this is the best score that it finds, and this is the combination of ingredients. So it's saying, okay, well, if you have 138 grams of apple and 112 of cow and 2 grams of potato and 26 grams of bacon, you'll get a distance from your ideal goal as per our scoring method of 18 points. Now, let's see what happens if I run it again. Now let me get rid of the alerts there. If I run it again, just remember the 18 as being the best possible thing that we could find. Oh, look at that now, 11. We're much closer. So our 18 solution that when we ran the test before was obviously a local maximum, and we've just found a better possibility. With, if you look at the composition too, it's quite different. It's not using any cow or potato. And let's see what happens if we run it again. So we had 11. Oh, so this time around we're getting the same thing. Let's try it again. How does the optimization work? Blue Barn asks. That's a very good question. I'm using, I don't know how far back, I was just explaining just all of that. I don't know if you just joined or, I'm using an algorithm called hill climbing. And, oh, look at this one, see, 13, different composition. So obviously what I'm getting at is I am obviously using this simple algorithm right now. I'm ending up at a bunch of different local maximums. Hey, no problem, Blue Barn. I'll recap quickly. So what we're doing is we're trying to get the best combination of ingredients that will get us to an ideal mix of nutrient goals. We're trying to see, given different ingredients, and their composition in fat, protein, carbs. And given my goal for this meal, I want to eat, for instance, 20 fat, 22 protein, 10 carbs. Well, we want the algorithm to spew out to give us the best possible combination, or at least close to the best possible combination in a reasonable amount of time. Now, that's often the problem when you're doing algorithms, right? If you're trying to get the optimal solution, it might end up taking way too much computational time. So sometimes you have to settle for good enough, and that's what we're kind of doing here. Although, when there is a small amount of ingredients, I think we can almost every time find the best solution, the global optimal. So the hill climbing, did you get the explanation of how hill climbing works? Because I can go over it again if you want. I don't mind. I aim to please. It's not too complicated. Well, in short, what we're doing is we're randomly generating a possible recipe, possible mix of ingredients. We're scoring that. We're comparing it to our goal, and we're giving that a value. And this is what the scoring function does there. Then we generate neighbors. So we increment, the weight, or decrement the weight on different ingredients, and then we score all of them. And if we find a better combination than the one we started with, then that becomes our next step in the algorithm. And then we just go all over again. We generate new neighbors, we evaluate them. Are they better? Yeah. And that's how we keep climbing up the hill, or in our case, descending, because we're trying to optimize towards 0. So that's basically it. Okay, and now I want to optimize this so that it works with more ingredients and gives a more consistent answer. If we were to run it over and over and over again, I would like it to get the, not keep spewing out local maximums, even though they're pretty good solutions or combinations. They're not the best ones. And okay, so one way of doing that is to just modify our algorithm a little bit, and let me pull it up here. I think I can find something quickly. Hill climbing. What's it called? Actually, if I go back to our Wikipedia page, I think they talk about it here. Invariance, yeah. So what we're doing right now is steepest descent climbing. That's my version of the algorithm. What we need to do is implement this random restart hill climbing, which is really not that complicated. We're basically going to run the algorithm several times, starting from a different point. The idea is that you would, doing that, avoid just getting local maximum, but eventually you'll find the optimal one. For instance, if I started off and just did the one-shot thing as I'm doing right now, and I started off right here, well, the algorithm would stop here, which is far from the best possible combination. But if I did it a bunch of times, starting here, starting there, starting here, starting there, starting here, eventually I would find the best one, or at least I would find a better solution. So that's what we're going to implement right now, and we'll see what happens. Okay, so I think we're going, oh, you know what? I think I found an example of that online. Let's do a quick search for Hill climbing. What was it called again? Random start. Random restart. Random restart. Nope. That's not the one I'm looking for. Let's see. Nope. Nope. Okay, well, whatever. I'm just gonna wing it. It's not that complicated. Basically what we're saying, right now we're running this every time. This is what we're accumulating, and this is where we're storing the best possible option. So what we need to do is tell while that we want to keep going until we run out of, let's call this tries. I'll change that later if I hate naming stuff. And let's say we want to run it, I don't know, 10 times. Okay, so now, while we still have this, now we're going to need to change this as well. Hold on, this might not work if I do it that way. Let's backtrack here a second. This little output to current recipe. So Blue Barn asks, so each time it's run, does it save a key value pair to determine where the most optimized point is? It does in essence. So what's happening here, this is where it stores the best recipe as it runs. This is, see how I've got up here, no, or is it, yeah, okay. So as it runs, well, okay, let's walk through it. First thing we do is we generate the neighbors of our current recipe. We start off the algorithm by generating a random current recipe. Then we generate the neighbors, which I'm storing in this variable here. I'm initializing next eval to just the biggest possible number in the universe. And I'm initializing this variable next recipe as just the current recipe for now. Now, what we do is we go through the list of neighbors. For each neighbor, we give it a score. We evaluate it and give it a score. If the score is smaller, because we're trying to optimize towards 0, that's true. So if the score is smaller than next eval, which of course on the first run it will be because next eval is the biggest possible number in the universe, then the next recipe becomes the neighbor, okay? And the next eval becomes our score. So that's, we just found a better score than next eval, so the next eval becomes the score of the neighbor. And now we check as well if next eval, which is now the score of the neighbor, if it was a better score, which on the first run it is, of course. If next eval is bigger than our current recipe score, which I should really be storing somewhere instead of evaluating every time, but we'll see. Then it means that we've found the best possible option, right? If the best neighbor actually has a worse score than the one than our subject, our current recipe, then we're done. We've reached a peak, and that's where we return the current recipe. If we haven't, though, it means that there are some better options out there, and we keep going. Current recipe becomes the next recipe. And then we start all over again. Hope this helps. So now what I want to do is all of this, I want this to happen not just once, but a bunch of times, starting from different places, starting from a different random recipe, randomly generated recipe. So how am I going to do that? While also keeping the best recipe, best possible recipe. So, you know what? I had found a nice little concise way of doing this. I think maybe I stored it on my tablet somewhere. You know what, guys? Just give me 10 seconds. I'll be right back. I'm going to go get my tablet, and I think I've got it stored there. It'll save us some time. And look at that. I'll even put my little be right back screen. And I'm back. Thanks for sticking around. Okay. So I did find it. So I had looked it up last night. And let's see if I can put it up on our screen here so you guys can see it. It's a PDF that I had found some. Let's see if we can find it here. Class 6L SS simulated annealing. There it is. Okay. It's got some pseudocode for different versions of the algorithm, and I found one that was pretty good, I think. No, I might end up doing this though later on, so we'll keep it. So I'm thinking of something else here. Oh, there it is. Okay. Zane Academy. Random restart. Hill climbing. It's a Zane Academy link. See it. How did I find this thing? Was it on the first page and I didn't? Oh, that's the one.
Good grammar and
but I don't
spelling
want
are
the.
important. But if you want to write essays that
It's on their WordPress. Zane Academy WordPress. Ah, there it is. Yes, and actually, okay, that's why I remembered. Let's do this. The screen capture is actually a pretty good example of what we're looking for, I think. Find shortest route. They're using that with the traveling salesman problem. But we can adapt this to what we're trying to do, I think. There we go. Okay, this is here. This is what we're looking for. Iteration toast. So they're putting that in the while statement. See, this is where they generate the neighbors. That's the equivalent of my generate neighbor function. I don't know if you guys can see this, if it's big enough. Can I make this bigger? Yeah. Maybe one more. How about one more? Whoa! Okay. So, right, so while we haven't reached our maximum number of iterations that we want, we generate the things. If it's bigger, if it's, well, hold on, if the total distance is smaller than the total, so okay, so if our current neighbor is better than whatever we had accumulated so far, what do? Iter to max, we reset the counter? And the current route becomes the new route. Else we increment it. Oh, okay. Oh, that's interesting. So it's actually putting a cap on one run of the algorithm. I don't know that that's what I want to do. Close and accept, yes please. Because if we do this here, from what I understand, we might actually stop before even finding a local maximum, right? If it's, oh, if it's smaller. Okay, if it's smaller. No, okay, so if this is true, we have reached our local maximum. We set this to 0. And we keep going. Right, current route equals new route, adjacent routes. And then we keep going. And if it isn't, so if we had found a better solution on a previous run up a hill, then we just plus, okay, no, I think that's gonna work. Let's try to implement that. Okay, so what are you saying here? So each time it's run, does it say like, oh no, answered that already. All right, let's implement this, see what happens. So we're gonna change this to, what did they have? Iteration to maximum counter. Let's just use the same wording to maxima counter is bigger than iterations before maxima. We need to set them somewhere. We'll just put that here for now. Oh, don't do some caps. Now let's make it, I don't know, 5, 10, whatever. Play with that later. And this should be set to 0 as well to start with. This needs to be 8. 0, okay. For the rest, I think everything gets to stay the same, except that now we need to modify we're generating our obtain adjacent route. Okay, so if we okay, this is where we're interested here, and we might need to flip this on its head. do this a little differently here. Adjacent route, obtain adjacent route. Oh, we would have to take a look at, they have that in a different function. Okay, I get it. So this here is actually happening in a separate method in the one I'm looking at here. Actually, all of this is happening in a different function, but we're going to keep that here for now. Okay, so once we've done that, if it's worse than the one we had before, this is where we switch our iter to maxima counter back to 0. And instead of returning, we set current recipe to next recipe. Right. If the score is better, yep. Okay. And now else, this is where we need to change this, else we increment our enter the maxima counter. And when we're done doing all that, we can return. We can return with confidence our current recipe. Okay, let's see what we get. I'm gonna move that here. Oh, it's not storing it here. So let's store it outside just so that we can log it first. We're interested in next eval. Well, let's just best score. Yeah. Just do that. Best score is equal to score. We'll just delete that later. Just so that's easier to see as we're running this. Okay. Obviously we did something wrong. Yeah. We have not improved things in the least. That is very interesting. Let's run it again and see what we get. $5.13. Now I'm thinking I might have screwed up on some of my... Alright, let's run through this again. If our neighbor's score is smaller than what we had here first, what do? Next recipe becomes neighbor. Next eval becomes score. And once that's done, we also check that next eval. If it's bigger than the score of whatever our best recipe was so far, we set iteration to maximally to 0, and our current recipe becomes the next recipe. Okay, this might be wrong. This might be wrong here. Next recipe, next recipe. What's the value of the next recipe here? It's the neighbor because the score was better, so that's fine. But why would next eval be... No, we've already determined that. Nope. I don't like it. Let's just go back, start from scratch. Well, not from scratch, but before I did it. This we get to keep. Okay. So what do we need to do here? What we need to do is whenever we get to this thing here, we don't want to return. We want to start all over again. Or basically we want to keep going, but from it, oh yeah, so this is where we want to start over again from a different place. How do I do that? Well, we could, there's different options here. Could use some kind of a recursive function. Recursive function could be interesting. A while loop inside a recursive function, why not? Let's just make sure we're back to a technically this should work still. Recipe. Recipe that customizes. Did I break something in my tests unknowingly? Function lacks ending return statements and return type does not include undefined. That's interesting. Didn't give me that problem when all I had was true in here. Huh. Very interesting. TypeScript is smart. So let's give it what it wants. This should fix it. Yep. Okay. Okay, well, so we're back to normal. Like around 11 was the best score we could get with the current version of the algorithm. Yeah. Try it one more time just for fun. Let's see, this one we're getting 17, so. All right, should I make this a recursive function or have some other kind of mechanism? Well, I need actually if I was to call the entire optimize function recursively, would that make sense? What are we taking here? We're taking a bunch of ingredients. No, I don't want to go to that. But this here, oh yeah, we could call it with the ingredients. We already have them. We're not mutating them or anything like that. So if here, no, that wouldn't work. Okay. Okay. We need a place to store, and we already have it. Our current recipe. Right now I'm initializing it with a random recipe. We're doing this, blah, 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 blah. If we get to that, that's what we need to change here. We need to say, we need to store that somewhere else. Well, actually I can use current recipe, right? It's already stored in there. So what we need to do is say, let's generate a new starting recipe and get going all over again. But here's the thing. This line here pulls from current recipe, which you know is fine. Except when we get to where we want to start over again. How about then? I'm going to pull that out into its own separate function. It's the only way I can reason about this. Let's get this back here. Rid of that. We'll get that from somewhere else. Get rid of this. Okay. Do I want to? Yeah, I do. That's like our base. That's our base function. What are we going to call this? We're going to call this base optimize. Change that later. It's a crappy name. Okay. So I need ingredients with max weight. Need to pass this in. And that's the type. For now. Okay, property map does not exist on type. Am I missing something? Yeah, it's an array. Okay, so this should work. And it'll return the recipe that we need. Comment that out for now. Actually, all of that like this. And this is where we call this dot base optimize with whatever we want, really. Oh no, we need to extract this. We need to extract this. So we'll just call this starting recipe. I need all of this. Just put that here for now. Okay. Actually, this can just be current recipe, and we can just use that. I don't need to current recipe. I'll type recipe, and this should work. Yep. Now all we need to do is pass in whatever current recipe we want. So, for instance, we should make this also into generate random recipe function. We're going to get a recipe from that. This is the logic. This is the stuff we're missing. And what's the type of that thing? We had it right here. Like this. Where'd you go? Where'd you go? Oh. Okay. Generate random recipe. We're not doing that. Yeah, need to return this like that. Okay. I think we're getting somewhere. Let's go back here. So this base optimize. So now we're going to wrap that into I guess a simple for loop for let I equals 0, I is smaller than, what are we going to call that? Tries and I++. Okay. So we're basically saying, I want you to try this a bunch of times. Tries equals 10 for now. Now this base optimize will return our best it should return base optimize ingredient weight. Should be returning a recipe, shouldn't it? Why isn't this of type recipe? We're passing in current recipe. We're generating neighbors, which is an array of recipes. Why isn't it typing it that way? Generate neighbors. It's being explicit with the type instead of just saying recipe. Yeah, whatever. As long as we're getting what we're supposed to get. And this is what we need to store here. Let best so far. We'll initialize that to this dot generate random recipe, passing in ingredients with max weight. Now we're doing that. Throw in the best so far. We're going to get best so far is going to become that. Oh no, see, this is where it doesn't work. Because once we run this once, we need to generate okay. Let's call this seed. Let seed recipe equals this here. Like that. We'll simply say recipe here. So best so far is equal seed recipe. Then when you're done with that, seed recipe equals run that again, and then we're okay. Okay. I think this will work, and then when we're done running all of that, we just return our best so far. Oh no, it's not that simple. I need to make sure that this is better than what we have so far. If this that base optimize seed recipe, let's just grab this, is oh, I gotta score it too. Okay, so this dot score, this is getting complicated. Pretty sure this isn't the most efficient way to do this. This is our score. We're scoring the result of this thing, which we're already doing inside. So that's, but it's not a very heavy thing to do. So if the score is smaller than this dot score of our best so far, it's used before being assigned. That's true. That's true. So let's do that the other way around. Okay. So if our score is better, then we can go ahead and take and make best so far become okay, I need to store this. Or no, that's a const. Candidate. Okay. If the score of the candidate is smaller than best so far becomes the candidate. And once we're done doing that, we generate a new seed recipe and we start over again until we're done trying, and then we return best so far. The thing is, I want to see the results, so let's log. Use our trusty score function. Best so far. Whoop. Okay, let's see if we have improved upon our solution or if we've messed something up badly. Oh, look at that. Ho, 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 ho. So I don't know if you remember, but the best we were usually getting was around 12. And now we've gotten 1 point, that's like almost perfect. It took a little longer to run. That's true. We can probably optimize that. And let's not forget that it's running with some other tests too at the same time. Running the test suite. But let's write this down just for kicks. So we're getting 1.54. Apple is 10 grams of apples. We're getting 0 of cow. We're getting 74 of potato. And I like that. I like that recipe. No cow, no apple, all potatoes, all bacon. Obviously, those aren't real. I just plopped numbers in there. 84 bacon. Okay, let's run it again. We're back to our 11 here. And again. Seven, that's better. It would never get 7 before. $11, 10. So 11 was the best score we would normally get before. Oh, 1.9. What does that look like? That's pretty similar to the other one we had, was 1.54. Right, apple was 10, now it's 15. Potato was 74, now it's 71. Weight was 84 for bacon, and that's what it is right now. So that's not bad. I would say it's an improvement. It's an improvement on what we had before. It could still be improved upon, and I'll be working on that maybe tomorrow or next week. I don't know, but I'm pretty satisfied with our progress today. So I'm gonna have to end it now, guys. Got some other stuff I need to go do. Thanks for sticking around. And I'll be streaming again next Monday, 9 a.m. Eastern Daylight Savings Time. See you then.